So I want to get you guys started right away on the second assignment for module number 4. And it's an inline slider crank mechanism where we're going to be predicting what the displacement is going to be, or the piston travel, if you would. So I want to go over that assignment for you because that'll be then rounding out this particular module, which is graphing with Excel. So so if we go into that second assignment, now I did give them each, like, graphing was the first one, and now this is the inline crank. So you distinctly can see you have those two assignments out there for module number 4. So here's the assignment, kind of the information. And I've got two handouts here, which if you're in class, you got those. Otherwise, they are PDFs right here. And I'll be pulling them up underneath my camera in just a bit to go over those. So that's going to be kind of the basis with what you're going to be working with. And then I have down here some manual inputs that you're going to be putting in, as well as what your displacement, or I'm sorry, what your outputs are going to be. And then you're going to create a scatter chart to plot what we're going to find out is the crank angle to whatever the corresponding piston displacement is going to be. Okay. And a couple of little notes here, really kind of going along with the same type of requirements we've had in the past or for the last assignments, just making sure to present the tabulated data and scatter chart in a professional manner that's easy to read. Include any labels that are required on the chart. So at the very least, you've got to put a title on it, and you have to label the axes with their units. And then just kind of making sure that you're watching this, because I give you the details and the requirements through this process of either attending the lecture or watching the recording. Okay. So you'll be uploading then your file to this. So let's look at the handouts that I gave you. I'm going to go underneath my camera here, and you'll notice that there are two handouts. So we have this first one here, and then we've got the second one. Okay, so let's kind of look at the first one and just kind of see what our requirements are, and then we'll look at the second one to kind of further explain. So the first handout that we have here is really a problem from our kinematics class. Okay, this is an inline slider crank mechanism. It's a standard 4-bar mechanism, and it really represents in simplistic form, if we would, most often, like, a piston is arranged up and down, it's going to be a crank, a connecting rod, and then, if you would, like a piston. So this is a crank slider mechanism, which is now, it's not the only place that something like this can occur, but it's a very typical application of this arrangement. Okay. And what we want to do is we want to determine what we call piston displacement. So we're gonna kind of lay this out flat, and we're going to find out how far, what they call it, if it was this way, what is the top dead center location? Then that would mean that all of these are in line, or how far it can actually travel away from what we call the frame. And then what we're going to do is we're going to rotate our crank around, and then we're going to find out, like, how that changes for every, you're going to find out for every 5 degrees of crank rotation. Like, I move this, from up and down, straight up and down, I move it 5 degrees. This is going to come down a little bit. Now, what is that new distance? And what is that new distance each and every time? Okay. So our next, the other handout is going to give us a couple more details, but that's essentially the problem that we're going to be looking at. Now, you'll notice that there are two equations down here, and those are going to relate to what you're going to be programming into your spreadsheet to get the data that you need for the output of the displacement. Okay. And so those are those two. Again, explain that in just a bit. And then I want to give you a peek at what you're going to be creating in your spreadsheet. Now, this is a screenshot, not of the entire tabulated data. You'll notice this starts with 0 degrees, it goes to 100, but in 5-degree increments, you're going to go all the way to 360. So it's one full revolution of this crank going all the way around. Okay. So we'll look at this in just a bit. Let's kind of get a little bit better explanation of the mechanism itself. So first and foremost, I have these staged, if you would. So the first arrangement is, as I had told you, where we have the crank and the connecting rod in line with one another, so that our piston, or our slider, is at its what we call top dead center. It's furthest point away from what this is referred to as the frame. Okay, frame just means that it doesn't move. Okay. So you'll notice here that using the dimensions of 1 inch for our crank and 3 inches for our connecting rod, that means that from our frame all the way out, that's 4 inches away. And that's where we're going to start. That's going to be called position 0 or 0 degrees on our crank angle, because this is going to be the furthest out that can be. It's going to be the highest point that it's going to go. That's our 0 degrees, if you would. It's not the standard 0 degrees like X 0 degrees. This is where we have our furthest point away, where our piston or our slider is in its fully extended position. Okay, so we're starting there. Then what we're going to do, so you'll notice down here, crank angle is 0, and then theta 3. All right, theta 3. So theta 3 is the angle that from our piston makes with the actual connecting rod. Okay, and back over here on that original arrangement, theta 3 is right there by the piston or the slider. Okay, and that if we lay this out flat, that would be 0 for that 0 degrees. Okay. Now, theta 3 can be calculated, because what's going to happen is as we rotate around, that crank is going to lift, and then this slider is going to pull back, right? If we're going counterclockwise, it's going to pull back. And what's going to happen is there's going to be an angle that's going to be created here. All right. And we can calculate that using the equation that we have down here. All right. So you will have a column where you calculate, and you'll notice down here, I have on the spreadsheet that I created, I have a theta 3 value. Okay. All right. So everybody following along with me. All right. Then as we move our crank, now what I did is you're going to be making your chart, you'll notice, in every 5 degree increments, but I wasn't going to draw each and every one of these at 5 degree increments and go, because that would be a lot. So I went to 45 degrees. Okay. So you'll notice here that it says crank angle is 45 degrees. So from where it was vertically, I now rotated it counterclockwise 45 degrees. And then I redrew where the new position of my slider would be. So you'll notice that it pulled down a little bit. Okay. And then the angle that original line makes with the connecting rod now is that theta 3. Now we actually have an angle here. Okay. And at that, when I rotate my crank 45 degrees, that angle is going to be 13.63. Okay. The reason I have this here is because when you do your calculations, you want to have something to verify, right? You want to make sure that you have it. So I'll pull this up, but this kind of gives you, let's focus. If I find where 45 degrees is that here? 45 degrees is right here. And I believe it's large enough on your handout. You should be able to read the values across. So 13.63 is our number in degrees for the theta 3. And that way, when you're, like I said, when you're creating this and coding in, you know, how to put the equation in, now you have a place where you can verify, like, okay, if 45 is good, that means all the other ones are probably pretty good. Okay. And you'll notice that very same thing for not only 45, but I did it kind of every 45 degrees. Now you're going to notice that my crank angle is 90 and you've got a theta 3. And then my crank angle is 135 from 0. And then you've got another one and so on. Okay. So, so this is for verification and also to identify where the different elements are. The next variable that you're going to be concerned about is alpha. Okay. Alpha is going to be the angle that the crank and the connecting rod make as we kind of rotate that connecting rod. So that'll be a calculation. Now, the equation that I have on here is actually this one. So alpha is equal to that variable. I don't know what that variable is. I just chose alpha because that's what I normally see. Okay. So, so alpha is this, and then alpha is that one as well. So it's between the connecting rod and the connecting rod and the crank. It's that angle right there is alpha. That's what I used for my chart. Okay. So that's going to be calculated using 180 degrees minus theta 2, because that's your crank angle, minus theta 3, which is this angle between the slider and the connecting rod. Then that whatever left over after subtracting those from 180 is going to be the angle of alpha. So that one's pretty straightforward. Okay. Then you're going to use that angle for alpha in the following equation. So this is going to be cosine of alpha. okay, down here. So that's going to be my length L4. Now L4 is the distance from the frame to where the slider is in its new position as that crank rotates. Now, because I had this going in this direction, I don't call that L4. I actually call that Y. That's my Y distance every time. Okay. So I'm going to call this Y. Okay. So that's my Y column, just so that you know that corresponds right there. Okay. Alpha corresponds right there. Theta 3 is right there. On mine, you may arrange it a little differently. Okay. Because you're going to be able to start this fresh. Okay. I'm going to show you how I approached it. You've got the equations here and you've got what you need to create as your output. And then now you're going to like go for it. Okay. You're going to make it your own. All right. So then you'll notice that here's my Y value. Okay. Here's that alpha 3. I'm sorry, theta 3. And then alpha is right here. And then again, corresponding to each one as we move the crank another 45 degrees. Now, those 3 are not your outputs, okay? They're used to get your output. Your output is actually going to be delta, okay? We want to know what delta is. So delta is the amount from top dead center. So right here, we call this top dead center. And you've maybe heard of that. It's a very common term when we're talking about position of pistons, for instance, in a cycle of an engine, okay? So when we're at that fully extended top dead center, that's our 0. That's where we're starting. And then we start rotating from that position. So when we rotate, we want to know what is the position, what is the pistons, sliders, displacement from where we started at top dead center. So delta is always being referenced each time we rotate from that original fully extended top dead center position. Okay. And it goes to here, right? That's the number we're interested in. That's the number. Okay. So when we look over here, delta is this column right there. So there's my delta. There's that displacement from 0 each time. Okay. And that is going to be on the y-axis here as we go through every 5 degrees along our crank angle. Okay. So you can see down at 0, we have 0 displacement because we're at that position. Then each time we rotate a little bit, 5-degree increments in this case, then it's going to increase that distance. And that's what we're plotting along the y-axis. Okay. All right. I don't know. Hold on, we're getting there. Okay. So I just want to make sure you understand where we're going with this and how this thing is. Any questions so far on the operation? I just want to make sure we all understand the operation and how the labels here correspond to the equations, and then just kind of pointing right now at my spreadsheet, like where things are located. Okay. All right. So let's look at my spreadsheet. Let's look at my spreadsheet. Now, you're not going to get this, right? This is like my way of expressing what we want to do. So really the goal here is we want to create a piston displacement versus crank angle scatter chart. All right. With the equations that we have here. So when we go back over here, the first 2 columns, the y-axis is first, the x-axis is second. I have those first 2 columns are the ones that are actually going to be plotted. Okay. There are going to be 2 inputs that you're going to put in. Well, I should say 3. There's 3 inputs, manual inputs, if you would. You're going to put in the length of your crank, which is L2. So if we go back underneath here, L2, oopsie, wrong one. L2 on my diagram is the length of member number 2, okay? Right there. So, and then you'll notice here too, L2 is the length of member number 2, and it's considered what we call, in this case, the crank. L3 is going to be the length of the other member. It's going to be the connecting rod right here. So L3 is equal to the length of member number 3. slash the connecting rod. Okay. Those are two inputs, and those typically change, you know, so you're going to have a different problem. You're going to have a different setup. And those two variables are very commonly, you know, going to be changing for you. But I did put a qualifier on my spreadsheet here in the just in kind of the instructions, if you would. Is somebody trying to get in now? There you go. Okay. And as we look here, you're going to notice that my L2 always has to be less than my L3. It can't be the other way around. The L3 always has to be larger than the L2. Okay. So that's like a condition that we have. And you'll notice that when I change these two numbers, my whole spreadsheet changes, and that's the whole point. So I'll put 2 in here, whoop, updated, and then I'll put 4 in here, and it automatically updates as well. Okay. So any questions, kind of like what the operation is going to be? All right. The additional piece of information I want you to grab is, what is the stroke? The stroke is going to be the difference between the top dead center and the lowest position that goes to, or bottom dead center, they call it, right? On a piston arrangement. So the difference between those two. And the stroke then along my displacement here is going to be the maximum amount of displacement, because that's always a measurement from 0. So for my stroke, you'll notice that I used that function of max down just this column. Okay. I want everybody's attention, please. All right. So I gathered it from this entire column here of my delta once it was created. Okay. All right. So let's look at kind of what I have set up here. So first and foremost, you're going to notice that you have the input portions, and then you're going to have your crank angle going all the way down. The crank angle is also manual input. You're going to be putting it every 5 degrees. I know it's kind of a pain in the butt, but it's kind of long. Okay. The more points you have on something like this, the more accurate it's actually going to be. Okay. So that's the good thing about it. So, so you can imagine if you were to draw, hold on. Oops. If you were to draw each one of these each time, which if you take kinematics with me next term, fall 2, you get to do it a couple times. All right. But every 5 degrees, that would be crazy town. Right. And then manually, you know, measure your delta each time, and then plot your displacement diagram. That would take way too long. And that's why Excel can be helpful here. Okay. So, so instead, we can then even go to it wouldn't be even a big deal once you have the crank angles in, do it every degree if you want to, right? Because Excel is gonna change it for us, or it's gonna update it. So let's go back over here. Now, what you're gonna notice is that you're gonna have to program the cells. All right. So let's start with that theta 3. I'm not gonna go over this with you. All right, because you have the skills. We've done some trig stuff. We've done programming of cells. We know about the radians. We know about parentheses and operations. So this is going to be something that you're going to have to troubleshoot. And that's why you have, if you would, the little answer key to compare at key positions, so you know if you're on the right track. Okay. So mine's kind of long, and I've got a lot of parentheses. That's going to be something you're going to troubleshoot. That's going to be for you to do. Okay. And you're going to use for that column this equation right here. Okay. This equation right here. Now, theta 2 here, just as a reminder, you'll notice I do have theta 2 in there. That's our crank angle. So that's always going to reference this guy right here. Okay. Now, I want to remind you for L2 and L3, because those are inputs on our spreadsheet and they're not going to move. So once you start copying this down and auto-filling for the, you know, the rest of the numbers, you don't want those to move. You want those to always go back to these two spots right here. So when you put them in, you're going to have to put a $sign in front of the column, the letter. And then you're going to put a $sign between the letter and the number so that you freeze. So as you go down, it doesn't increment either one of those. You're going to go only to that cell. So it has to be $sign, for instance, minus $sign F3 divided by $sign F, $sign 3 divided by $sign F, $sign 4. to get that in there. So any reference that you have to an L2 or an L3 is going to be anchored both in the column right before the letter and right before the number. Okay, right before the row, because we want it to always go back to that same spot. We don't want it to increment. Okay, so that's theta 3. The next one that you're going to do is going to be your alpha. Alpha is over on the end here. Okay, alpha is simply going to be 180 minus the crank angle minus theta 3. Okay, it's just the interior angles of a triangle. So if we go back over here, here's our crank, here's our theta 3, and then here's alpha. So it's just a triangle. It's just 180 degrees minus the 2 that we kind of know already, right? So that one's pretty straightforward. But what'll happen is once you get past 180, it'll start going negative values. What you want to do is you want to avoid that. So what we're going to actually plot is the absolute value. Okay, so you'll notice that I put in front the function equal to ABS, absolute. And then that keeps those values positive all the way down. Okay, and you want that for your crank angle for alpha. And then you also want it for your delta. Okay, because you don't want your delta numbers. They're not really negative. They're always measurements from that same place. They'll calculate negative as you get on the other side of it, but the actual values themselves are still always a difference from. Okay. Theta 3 is not an absolute value. Leave that one alone. Otherwise, that'll kind of screw things up. We need its negative as it gets on the other side. Now, y, okay? Y is also not an absolute. The only two that are absolute are going to be the delta and the alpha. Oh, just those two. Okay, now we're going to look at y. Y, if we go back over here, this was the difference between where my frame was and the, whatever the furthest part out was for my value. Just want to make sure I have everybody's attention because there's a lot here for this application. Okay. So L4 is going to be this distance. I called this Y again because the arrangement that I'm kind of mimicking is going to be a piston, and that's a Y distance to me. It's vertical, right? So L4 to me is a Y distance. That's going to be the equation that we see here. And at the end, our cosine is going to be the alpha value. Okay. All right. So that's Y. Back over here. And again, kind of a big long equation. And anytime that you're referencing the L2 and the L3, you have to put an anchor, the dollar sign, in front of the column, the letter designation, and then between the letter and when the number starts. Okay, so any of those. And then also remember, anytime you're dealing with cosine or sine, the values are going to be in radians, or you have to convert the angles to radians by either using the radians function, right? Or your value is going to come out in radians. So then you have to, change it to an angle. So remember how we did that before. If not, you can look back. Okay. So I'll let you play with that a little bit because that is something you have to keep in mind. So that's going to be our Y. Okay. Now, none of those three values are really what we want. Okay. So let's look at the delta. The delta is not a really hard calculation. What it ends up being this Y value. And what you're going to do is you're going to subtract off the addition of these two together. That's all that it is. So it's in this case, I'm a K4 minus my two inputs added together. Okay. I'm not going to don't even worry about mine. You're going to put it in different cells. Doesn't even matter. Doesn't matter. Okay. Now, once we have those values, okay, once we have everything all set here, and again, this is kind of your little, I don't want to say it's a cheat sheet, but it's your checker. So be sure that your input, that you have the right equations. So make sure that you're using, for instance, I have 1 and 3, and then that's going to set me up so that if I check my theta 3 angle at 45 degrees, I want to make sure that it matches, right? And then you also have, this one for a match as well, so that you can kind of see physically where each one of these values are. Okay. All right. Now, creating the chart. over on the right-hand side, I've got my chart. And when you make your chart, this is going to be a scatter chart. It's going to be like the stress strain diagram. Okay. So you are going to have a title on it. I called it piston displacement versus crank angle. Okay. And then you'll notice here that your piston displacement, and I just clarified, like from top dead center in inches, is going to be the title and the units for that y-axis. And then my x-axis is going to be the crank angle in degrees. Okay. And notice I've got a lot of points on here because it's literally every 5 degrees, right? Because that's how I set up that first column. Okay. And then that's it. Okay. So the challenge in this is not so much, I don't think it's a hard thing, you know, to understand like what's going on. I believe the challenge is in getting those a little bit more complex equations going. So like the theta-3 and the y are kind of big equations. All right. So the deal here is going to be parentheses and making sure you separate things out. So I have quite a few parentheses, and then also the radians and then the conversions back into degrees when you need it. So so that's going to be probably what you have to play with a little bit to get the numbers. Okay. And that's really part of what I want you to do. I'm being a bit, I don't want to say I'm being a bit vague. I think you got all the information that you need to finish this assignment, but now I want you to kind of take it from here. Okay. I kind of set it up like this. You may have other ideas of how you want to set it up. Be creative. You know, I fully want you to do that. And additionally, really what I want in the end is I want a displacement diagram that is going to plot for me, and you can show me the piston displacement versus the crank angle. Okay. So however you set up your tables, as long as you can get the correct values and you can verify them here, then you're good to go. All right. And I do want it, you'll notice if we look back at our assignment, your manual inputs we have here, outputs, as we just talked about, create that scatter diagram, and then make sure to present the tabulated data and the scatter chart. I'll wait until we're ready and we're listening. Make sure that you do it in a professional manner that's easy to read and also easy to use. Okay, that's part of it. And then include all your labels in the chart. I kind of put that as an extra little note there. Questions? Okay. That's what I have for you today. Oh, yes, Eric. I don't know the shortcuts. How I did it each and every time when I put them in is I went to insert and symbols, and I got them from here. And then Greek C, I was, if you put in the font up here, I think it defaults to something else, but Greek C, Greek-C, it'll come up with kind of the fancy ones. All right. Yeah, that's how I input them. I don't know. Maybe there is a shortcut to it. I'm not sure. Oh yeah, that's what it would be. You could do that too if you wanted to. I just find this way because I don't necessarily know, because sometimes like alpha goes with A, but sometimes it doesn't, you know, depending on if it's capital or if it's lowercase, I think. I don't know. Okay. And please put them in, you know, make that attempt to put in theta, because those are symbols that are universal. If you would, kind of in engineering, you see those come up a lot. Don't just kind of put something in. Yeah, I think it's time to take the, you know, make the effort to put those in correctly. Any other questions? All right. This is not a terribly hard assignment. Like I said, I think the challenge is in getting the more complex equations put in, and then from there, I think it becomes pretty straightforward. Okay. All right. So so that's our second assignment. On the calendar, I have it due tomorrow, which is Friday at the end of the day. Again, target due date. So if you do need extra time, you certainly may take it. But I think you should be good if you work, you know, during this time. Be good. Okay. I'm gonna stop recording.